Good morning. So I would like to present my recent works on coherent quantum transport of microcavity Exciton Polaritons. My name is Sanjeev Ghosh. I'm currently working at the Chinese University of Hong Kong in their Shenzhen campus. So our main campus is in Hong Kong, but we have a new campus in Shenzhen, China. So here is the outline of my talk. So first I will discuss what is quantum transport, particularly for Bose-Einstein condensation, and introduce diffusive motion, Anderson localization, scaling theory, and boomerang effect. Then I will go into the quantum transport of Exciton Polaritons, and I also disorder scattering, and then which leads to this quantum transport leads to anomalous localization, which we think is extremely interesting. And then I will also show that this creates opportunities to study these anomalous phases with spin dependent effects and other effects in Exciton Polaritons that is available, which might not be available in other Bose-Einstein condensation systems. And then I will also show some of our experimental efforts that we have worked in Beijing last year. So Bose-Einstein condensation was proposed by Einstein based on a theory developed by Bose, that leads to this Bose statistics that follows by bosons. And Einstein actually have seen or noticed that there is a negative sign in the denominator, which indicates that the number of particle in certain energy level can be extremely large or macroscopically large if right condition is achieved. And so these large number of atom in a single quantum state is now known as Bose-Einstein condensation, and it is typically formed in ground state of a system, and it was first experimentally observed in cold atomic systems by Eric Cornell and Wolfgang Catterley. That required laser cooling, and which only can possible to get a BEC in a mesoscopic scale. So even we can say microscopic scale. So it is not possible to really go to a macroscopically large number of particle in a quantum state, and it also requires extremely low temperature. So Exciton Polariton in microcavities, that I guess that you have seen already in this conference, and that we have these particles in microcavity structure, and that can also undergo Bose-Einstein condensation. So there can be some certain difference with the ultra cold atomic BEC, but anyway, the main feature that the large number of particles in a single quantum state can be achieved in Exciton Polaritons system even at room temperature, and that has been reported by many groups now. And details of these Exciton Polaritons can be seen in this beautiful book written by Professor Kavugin and his co-authors. And also I would suggest to look at this our recent review paper published in Photonic Insights for recent developments in this field. Now, earlier, quantum transport of BEC, particularly for cold atoms, was explored by Alan Aspect group, who got Nobel Prize a few years ago in his contribution for quantum optics and quantum information. So what they did is that suppose I have a cloud of cold atoms, and that is moving in a disorder system. So this disorder can naturally be present in the various systems, in almost all physical systems. And then this atomic cloud, if it has an initial momentum, because of disorder scattering, in the direction of the momentum will change. And if the disorder is quite random, then the direction of the final momentum will be in all possible directions, and that creates a distribution in the momentum space like a circle. And this is the classical Rayleigh scattering in momentum space. However, what they saw in extra is that when they start from a single momentum in the momentum space at time zero and then go toward through different times, at the end they have this classical distribution, isotropic distribution that we can call diffusive distribution, and on top of that there is a peak in the direction opposite to the initial momentum, and that is known as coherent backscattering. And so this is a feature of quantum transport that requires phase coherence. Not only that, they also observe what is called the Anderson localization. So because of these quantum interference effects, these interference effects is very strong, then what happens is that if we start with the atomic cloud, which is localized in a certain point, then with time it will expand due to the diffusion. It will expand in space, but after a certain time the expansion gets stopped, and this natural stopping of the expansion or the diffusion is called the Anderson localization. It was observed by this in 2008, and actually this is also associated to a new peak called the coherent forward scattering peak, so which is similar to coherent backscattering peak that appears in this Anderson localization system and was predicted by theory and have not been observed yet because of time scale issues. But anyway, so this indicates that this Anderson localization is because of the a coherent effect, and because of coherent interference, strong coherent interference. So now, how to characterize quantum transport? So typical signature of Anderson localization is the halt of diffusion and coherent quantum interference. So if we want to look at the halt of diffusion, then we can look at this diffusion equation. That is the x square average. X is the position. X square average is proportional to a constant called diffusion constant and t to the power an exponent nu. And so for diffusion, this nu is 1, and so therefore this x square average, or the spread of the wave packet or the atomic cloud, is proportional to the time t, and that is the typical signature of diffusion. And if this exponent tends to 0, then we will have a halt of diffusion, meaning that this x square average will not expand anymore with time, and that is the signature of Anderson localization. So this was studied theoretically for atomic cloud, that for classical diffusion it increases with time, this position square average, that is the spread of the wave packet or the cloud. And for Anderson localization, the spread of the wave packet doesn't increase with time, and it is experimentally verified for cold atoms. And so we can see for Anderson localization, the spread is not changing with time, whereas for diffusion the spread of the wave packet is increasing with time. On the other hand, it has been also studied that the center of mass of the atomic cloud, that is quantified by the x average. So this is x square average, this is only x average. So this is the center of mass of the atomic cloud. That is equal to L. This L is the scattering length times 1 minus exponential t by tau, and this is tau is the scattering time. So we can see that at large time this is becomes 0, and what we have is the scattering length. So classical diffusion predicts that the center of mass will first increase with time, and then it will become constant, and this constant is the scattering length. Whereas Anderson localization actually predicts that this center of mass should be 0, and this was predicted theoretically sometime in 2017, is that first the center of mass will increase like classical particle for Anderson localization, and then it will decrease and will become 0 at long time. So meaning that the quantum cloud will first go in forward direction and then come back to the center position or the initial position. So this is the signature on which is called the quantum boomerang effect of quantum transport. Now, another characteristic of Anderson localization is the so-called scaling theory. So, in scaling theory, you can construct a conductance, dimensionless conductance, which is related to this spread x square average and the time t, and you can define a length scale which is lt, which is square root of x square average. So this is obviously a length, and then using these two we can define a scaling function beta, which is logarithmic derivative of this conductance g. And the single parameter scaling theory says that beta is only a function of g. So it has been predicted theoretically and verified by numerous experiment and theory is that Anderson localization follows this single parameter scaling theory, that is the beta function or the scaling function is a function of only the g, the conductance. And so in 1D there is a universal in different dimensions, so d is the dimension. For different dimension there is a universal scaling function. Any system in the world will just follow this scaling function no matter what disorder, what time, what other parameters, and so on. So this is a defining factor, and so then people are trying to understand what is the effect of nonlinear interaction, because in atomic cloud we also have nonlinear interaction and it follows the GP equation. So if the nonlinear interaction is strong, then it has been shown that the single parameter scaling theory breaks down. So this is the scaling function for non-interacting particle, and as interaction increases we can see it goes back towards a finite value of the scaling function, and this region is called the subdiffusion because it's for localization the scaling function should go towards negative infinity, but it doesn't go towards negative infinity, it goes towards a finite negative value, and this is subdiffusion. This is diffusion, so it's a slower diffusion, and this is due to the destruction of Anderson localization due to the nonlinear interaction. Same thing can be observed in this center of mass motion. So we can see if it is non-interacting, then it will follow this green curve, and that is the Anderson localization. It goes to 0 at long time. On the other hand, if you have interaction, and it has been seen theoretically and experimentally later that it doesn't go to 0, it reaches to a steady value, and this is because of this dephasing effect coming from this nonlinear interaction. So it partially destroys the quantum coherence, and that is observed here. So we can see that these quantum coherence and this breakdown of scaling from single parameter scaling is a typical signature of breakdown of Anderson localization theory. Now, for Exciton Polaritons condensation, not only we have this Gross-Pitaevskii equation that includes this nonlinear interaction, but also we have decay. So the polariton can decay, it has a finite lifetime. We can inject, of course, new polariton. So and the details can be found in this book and the review paper. Anyway, moving forward, we would like to know how this interaction and the laws interplay in this quantum transport, and that has not been and that is not done in cold atomic system, because this loss is not that important in cold atomic system, but for our Exciton Polaritons this is an important factor. So what we do here is that imagine that we have a cloud of Exciton Polaritons that is launched in the system with the initial momentum k. And now what we are doing, we are tracking the width of the population, that is this x square average, and the center of mass of the population, that is the x average. So naturally x average will increase with time, and the x square average will also increase with time if this is only a diffusion. But now we have this quantum coherence in the system, and so it should be modified, and then maybe we will be able to see the Anderson localization. So what we do here is that this is the now we consider an one-dimensional case, so it can be quasi one-dimensional also. So suppose that we have a elongated microcavity, and this is the direction of the microcavity elongation, and this is time. So we can see that if we launch a Schrödinger particle means that the nonlinearity is zero and also there is no decay. So we can see this is the usual Anderson localization theory. So we can see we launch a particle around the center, and then as a function of time, the initially something happens of the center of mass, but then it comes back, and the center of mass is now at the zero, and the spread of the wave packet initially something happens, then the spread of the wave function, the spread of the wave packet is actually quite stable and it doesn't change with time. On the other hand, for GP particle, we can clearly see that as a function of time, the spread of the wave packet is quite increasing fast. So we can see that at the time picosecond t equal to 80 picosecond, the spread of the wave packet is completely as large as the system size. On the other hand, for Exciton Polaritons, where we have interaction and also we have the decay, and we can see that initially it is spreading a little bit more like the Gross-Pitaevskii particles, but then after that it doesn't follow the Gross-Pitaevskii train, but it more like the Schrödinger particle or non-interacting particle. So we would like to now see what is happening with the Exciton Polaritons. So we can see the critical this diffusive exponent should be 1 for classical diffusion. For GP particle, these particles we can see clearly that it is less than nu is less than 1, so that is the subdiffusion, but anyway it is a steady diffusion like behavior. On the other hand, for Schrödinger particle, these particles we can see that the critical exponent is initially decreasing with time and then approaching towards this Anderson localization behavior, that is nu is approaching to zero. For EP particle, it is something in between, so it is prolongated time dependence, and so maybe it is going towards some localization behavior, and we would like to see what is happening in more quantitatively. So this is why we calculated the scaling function as a function of dimensionless conductance, and we can see this is the single parameter scaling theory of Anderson localization. So this is followed by the Schrödinger particle when we do not have any interaction or decay. On the other hand, for GP particle, it initially follows this single parameter scaling, and then it departs due to the interaction, and then it goes to the subdiffusion regime. For our Exciton Polariton, what we see is that there is some initial similarity, but then it follows towards like GP particle and then comes down towards the Schrödinger particle. So in the longer time, it behaves like some kind of localization behavior, but clearly it doesn't follow the single particle scaling theory that Schrödinger particle follows. But anyway, from these similarities with this Schrödinger particle in this region, we can conclude that Exciton Polariton is showing some localization behavior. But is it Anderson localization? Because as we can imagine that because there is decay, so interaction effect will be decreasing, and therefore it will be more like Anderson localization. But then we looked at the center of mass movement. So for center of mass movement, for Schrödinger particle, it initially increases and then comes back to zero, and that is this quantum boomerang effect. For GP particle, we can see it increases and then it doesn't decrease to zero because of the nonlinear interaction, and this is the typical signature of destruction of quantum coherence. However, for exciton polaritons, from here we concluded that this is like an Anderson localization, but here we can see the exciton polariton center of mass is nothing but like the Anderson localization. So it should go to zero, but it doesn't go in. For exciton polariton center of mass is not zero. So it is behaving more like Gross-Pitaevskii particles. So from this thing, we conclude that exciton polariton is more like the GP particle. From here, we see the long time behavior is more like Schrödinger particle. So that's why we call this phase as an anomalous phase. And so we wonder what is happening. So far, our understanding is that the um, beta function or the scaling function is actually a signature or a byproduct of the spread x square average. And the x square average is largely affected by the wing of the distribution. So we have this the intensity distribution or the particle distribution or the wave function square, the intensity, and the x square average is largely affected by the wings, where the number of particles is actually quite low. And so therefore, because the population is low, the interaction is low, and therefore the x square actually behaves more like Schrödinger particles system. So, and because it is more like Schrodinger's particle, so it shows this Anderson localization behavior. On the other hand, x average, that is the center of mass of the cloud, that is in this region where the population is the maximum, and therefore because the population is maximum, the interaction here is non-negligible. So here the behavior more like the GP particle, and therefore it shows the subdiffusive signature in the x average or the center of mass motion. So we must not think this exciton polariton like Anderson localization. It is very critical. So although the wing behave like Anderson localization particle, but the center behaves like the like the GP particle, where the quantum coherence is already lost, at least partially. Now, I believe that we have new opportunities in this study of quantum transport in exciton polaritons, which has not been studied so much in this context. And so I believe that because exciton polaritons have various exotic features, and therefore we should have more opportunities. So in particular, I would like to report that a few years ago, we have studied this experimentally with the group of Professor Chihua Xiong, and to that prove that we can really track the exciton polariton motion of a exciton polariton initially injected at certain point, and then we can see it as a function of time. We can see at time t0, all the polariton are here, and then as a function of time it propagating along certain directions, and then we could measure the velocity of the polaritons and then compare it with the velocity extracted from the dispersion, and we see that they are matching well. So such is showing that it is the transport is possible to measure. And then we also proved that there is long range coherence, so it is a quantum transport, there is coherence, so therefore this behavior like localization and subdiffusion, all this behavior is possible to understand or observe in this system. Moreover, exciton polaritons has spin dependent features. For example, this famous optical spin Hall effect that was proposed by Professor Kavukin and others, and then was experimentally observed in 2007 in gallium arsenide systems where the temperature is very low, And now we recently we studied it in room temperature system, and then we observed this spin, and the direction of momentum is locked in certain directions. So we can see that the spin is momentum. This is momentum space. So we can see the spin distribution is related to the direction of momentum. So this is the spin Hall effect of Exciton Polaritons. So we believe that this type of spin dependent behavior coupled with these quantum transport properties can be a ideal direction to explore more interesting features. And anyway, so using this feature, we have proposed a NOT gate and a polarization beam splitter, and these two optoelectronic devices, which can work at room temperature, and is reported in Nature Materials in this year, collaborating with Professor Kabukin and Chihuahua and myself. Finally, we would also like to report that because Exciton Polaritons is a non-Hermitian system where we can inject new particle and old particle can decay, and therefore it is a highly non-Hermitian system where we can also study the transport properties with these non-Hermitian features. And so quantum transport can be enriched by these. For example, recently we have shown that if we use these TMD materials, 2D materials, transition dichalconides, where we have strong spin orbit coupling, and that leads to valley spin locking, meaning that the valley index and the spin index becomes strongly coupled, so that the spin at different valleys of the momentum space is actually emits different polarization. And so if we put such a material in a microcavity, we can see that because of the spin valley locking, the particle with a negative spin will propagate along these directions, and particle with the positive spin will be created with negative momentum that is propagating in this way. And this is a gain material. So these things is a non-Hermitian term in the Hamiltonian, and this is different from the coherent term like spin orbit coupling. And so this vanished spin locking gain, and together with spin Hall effect from the DBR, and we can induce G-man splitting by the magnetic field, we predicted that as a critical skin effect will appear, and that will lead to a quantum phase transition that shows that if we change the detuning, the spin current will change with the detuning, and it will change critically, so that if we plot all the curves obtained at different time will cross each other at a single point, and that can be identified as a critical point of a phase transition. Below this detuning, there will be no spin current, and above this detuning there will be a finite spin current. So this is our prediction so far. So let me now summarize that we propose that the quantum transport of BEC is an interesting topic, and it leads to a non-trivial anomalous phase of quantum Exciton Polaritons, and it is neither local Anderson localization nor subdiffusive system. So it is a mixture of both, and I believe this is a new phase, and it is possible to directly measure the Exciton Polariton transport in that is real-time tracking. So we should be able to observe such behavior, and the spin-dependent behavior and the non-Hermitian effects add new dimension for us to explore in the context of quantum propagation or quantum transport of Exciton Polaritons. So with this, I would like to thank you for your attention, and listening my work. And I would like to now invite you to ask question if you have about my work.